Greetings and welcome, friends. Mr. Waddy here. We're taking a look at page 116. We are reviewing reasoning and proof. This has been our first chapter, really digging into this idea of being able to use different types of logic, being able to use postulates, theorems, definitions, properties as a means of justifying step by step why we know something is true, or how we could even use those to discover something new is true that perhaps we didn't have any presuppositions about. So here I'm going to go over just a couple of the problems, I guess a few of the problems. Here we go. So let's see. What conclusion can you make about the difference, so that means subtraction, of any two odd integers? Okay, very good. So let's see. So if I have, let's just do 3 minus 1. Those happen to be consecutive odd integers. I get 2. Let's just keep trying some examples. Let's try 5 minus 1. I get 4. Let's try some different ones. 7 minus, what if I try a negative odd integer? Negative 1. That's the same as 7 plus 1, which is 8. And let's see, I don't know if you guys are noticing any trend yet. This happened to appear to be some type of a pattern, but notice that there was no consistency in my selection there. Let's see, if I try 5 minus 21, see, that's the same, signs are different, so what are the 21 minus 5 is 16, and I would take the sign of the more influential, which was negative. So here's just a small sampling, but based on this kind of pattern that I'm seeing, I notice that all of these are even. So here's my conjecture. All right, conjecture. The difference, yeah, I don't know, sure, there we go, of any two odd integers will be even. Integres are even. Okay, so that's my conjecture. That's based on a pattern that's not an actual proof. That's inductive reasoning, not deductive. Although theoretically, if you want, I find this interesting. Here's a more legitimate proof. If I let these two variables be integers, m and n, this would be one odd integer, and here's another odd integer, 2n plus 1, where m and n are elements of regular integers, so m or n could be even. And if I subtract these two things, this one's odd because doubling any integer will make it even, adding 1 to it will make it odd. So here are two odd integers. If I subtract these things, let's distribute. So let's see, 2m plus 1 minus 2n minus 1. Let's see, my plus 1s and minus 1s cancel out. I'd have 2m minus 2n, and now I'm suspecting that this is even, and actually I have a means of proving it. I can steal a 2 from both of these. Let's see, I'm working in blue here. So that's going to equal 2 parentheses m minus n. And since these were both integers, their difference will be integers. That's actually, that concept is the fact that integers are closed under the operation of subtraction. Where if you subtract two integers, you will get another integer. And 2 being multiplied by that, it's suggesting that 2 is now a factor of my new number, which was the difference of these two odd integers, and this one is even. All right, so that's kind of like a little bit more of a formal proof if you wanted it there. Let's see. Use the diagram at the right to determine whether you can assume the statement. Points F, B, and G are collinear. Let's find out where these are. So here's F. So F just happens to exist somewhere on plane P there, right? Here's G. G happens to exist on that plane. And here's B. Yeah, there we go. And it looks kind of like I could imagine from this perspective that those are in a line, but I do not know any of that. I cannot conclude that. I cannot assume that information. Based on what's shown here, there's no line that was drawn between them, so I can't prove right now that those are collinear. So, so the answer is no. No, you cannot prove that. Let's see, let's look at another one here coming at you. 15. So let's see, for question 15, we were to draw this picture. So let's see how well I can do. So two planes, P and R, intersect perpendicularly in XY, the line. Okay, that's actually, I feel like that's phrased a little bit weird. But to draw two perpendicular planes, I'm going to draw, here's one plane getting started here. Let's see, let's get a different color for the other plane. So I'm going to just make like a plus sign here. So crossbar those. So that way this is implied as being perpendicular. And if I connect these, so here's my plane. We'll call this plane R. We'll call my yellow plane plane P. And the intersection between these two planes we know is going to be a line. And in this case, we are defining that line as XY. So XY. X and Y can be just anywhere along this. So let's say that's X. And this is Y. All right. And then let's see. So, and then ZW lies in plane P. So here's an additional line that's going to exist in this yellow plane. It's going to be unique from the other one. It could just be kind of any sort of diagonal. It doesn't necessarily meet XY at a perpendicular angle. But let's see. So ZW. Oh, and actually, oh, I messed up. ZW is a segment, not a line. So it starts and ends at both Z, Z, and W. All right. So something to that effect. This doesn't necessarily bisect any of those things, so we can't assume those things, so don't. Let's see. Question 26. Write a proof using any format. I'm a fan of my two-column proof, so I'm going to set up. Here we go. Here we go. I got my Let's see. That's 90 degrees. Let's set up my two columns. Very good. I like it. So over here will be my statements. Over here will be my reasons. This sketch is from a little bit further up on the page. It took me a moment to find it, so I understand if that might have been a tricky thing to do. But let's see. So for question 26, let's write down what I know. I know that angle 3 and angle 2 are complementary. All right, the reason that's true is given. So in my little sketch, I know that angle, in this case, this doesn't at all look to scale. But if I knew that those two angles add up to 90, okay, complementary. Very good. I also know that the measure of angle 1 plus the measure of angle 2 equals 90 degrees. Let's see, 90 degrees. That was given to me. Okay, so 1 and 2, their measures add up to 90 degrees as well. So if I know that these measures add up to 90, I think I can make the claim that angle 1 and angle 2, they're the angles, not the measures, are complementary. Why do you guys think that's true? Well, that's going to be true because of the definition of complementary angles, right? If their measures add up to 90, then the angles are complementary. So this is def of not Kong, but complementary, right? Def of complementary angles. All right, and now let's see. So I've got these two angles are complementary. These two angles are complementary, and I notice, ooh, check this out. Angle 2 is in both of those. So that means angle 3 is complementary to 2, angle 1 is complementary to 2. I believe I can say that angle 3 is congruent to angle 1. And I'm going to use one of my previously proved theorems, which was the congruent complements theorem. And theoretically, even if you didn't know this theorem, you could have reproven that theorem in this problem. So the idea behind that theorem is this, that if two angles are complementary to the same angle, they must be congruent. And the way I like to think about it is, if angle 3's measure plus 2 adds to 90, there's no other angle measure that I could add to this one that would equal 90. It's not possible. That's the only way that it could happen. All right, so hopefully you guys are coming together and understanding this chapter. Proofs take a while to grasp. We'll continue to rehearse those things throughout much of the rest of this course, really. So you'll get kind of more into the routine of things, but right now, hopefully you're becoming more and more familiar with how they work. All right, well, thanks for watching, Internet friends. Have a great day. Bye-bye.